Thank you very much to the AEBC conference for letting me talk today. My name is Wenzel Prochazka, and I'm the Senior Product Manager at AVL for battery system development. I'm responsible for business development and strategy on our battery development group. And I want to talk to you today about the continued glimpses into the xEV batteries on the market, especially the topics of safety and safety integration that came up in our series battery benchmark program. So who is AVL and why are we talking about this? We're an engineering company, we're an engineering service provider with approximately 11,000 people worldwide, thereof about 400 to 450 for battery development. And we're very innovation focused, so we're trying to drive the market and we're trying to drive the technologies that come to the market. With that, we can support you in battery development from the benchmarking and concept development, concept integration of new technologies over the systems engineering and integration to a complete simulation virtual validation tools, to prototype build and even design for production process validation with our newly opened Battery Innovation Center here in Graz. So we have completely automated machinery, as you can see in the rendering still, but it's now in operation since April this year. Module stacking, laser welding, gluing, sealing, everything like that on fully automated 6-axis robot stations. This means we're actually covering the battery development and the battery life cycle that you have as an OEM from the inception of the technology that is going into the series development later on, over the development, over the safety, the performance, the cost, the production, up to the topics that are in field like serviceability and then recycling and design for recycling. And very clear also the CO2 life cycle is a topic for us. But today we want to look at the benchmarking, and we want to look at batteries that we have seen in the last iteration of this talk already, like the Porsche Taycan, Neo S8 and then Tesla Model 3, with a new contender this time, a fourth contender, so up to now I only had three, this time I have actually four, the BYD Han. Very interesting pack because it is LFP, the others are NMC packs. It is a cell-to-pack approach. It is approximately the same size as the Tesla Model 3 pack in terms of usable energy capacity. But you can see it has a higher voltage than the Neo and the Tesla with about 570 volt nominal, which is more closely from the electrical design standpoint to the Porsche. That's why I left it in here for some electrical safety comparison. And very impressively, it has more than 80% pack to cell weight ratio. So 83 point something. And this is why we're today comparing this pack to the others. Especially I want to take out of the benchmarking process, you can see there is a lot of work package from the vehicle all the way down to the cell tear down. I want to take out the topic of safety. This safety is on the one hand side the integration safety, on the other hand side it is also cell safety, electrical safety. And we're going to compare the pack on a couple of those measures. So first of all, I want to go on the vehicle side, and yeah, today with the recording I don't have the videos like in the last iterations, but I have pictures here, and you can see that or at least it should give you the impression that on the Porsche Taycan and the Neo, the vehicle is stiff. The battery is stiff, but it's still more of a take the force and absorb the force on the side seal measure. The Tesla Model 3 actually is a very stiff vehicle. So actually the side crash has the need for a side curtain for your heads and so on in airbags. It is a very stiff vehicle. It really bounces back from the pole. You can see that in the video here, not so much. The BYD Han is a very conventional vehicle in that regard. It is a quite soft vehicle. It absorbs a lot of force, and it has a battery integration that is, by the comparison of the screw lines, actually interesting because it has, and I don't know if we can see this here. On the side, beside the screw integration, this is this red line here. On the side, it actually has also the cooling channels for the cooling pipe work for the rear e-motor before it actually goes into the side seal area. So there is, even if the battery is mounted, there is an exposed cooling pipe work here, and on the other hand side, there is an exposed line also on the other side of the battery. So a little bit different integration. The other three vehicles, you can see that the integration of the pipe work, if there is any, on the Tesla you can see it stick out, is on the top of the battery side. So there's a side seal, the battery, and the pipe work is on top, protected from the underfloor of the battery. So a little bit different integration here on this vehicle than on the other three. In terms of distances to the side seal, we can see that the pure distance from side seal to battery pack is rather on the conservative side. So Neo and Han are around 165, 170 millimeters, versus Taycan and Model S are around 120 to 140. On the other hand side, it seems like there is not so much on the side of the battery, as the side seal to cell distance actually is below 300. So here it's not the most conservative, it's actually somewhere in the middle game. But it is, as the two others that have rather distanced side seal to cell distances, it is a prismatic cell, and it has the tabs on the sill side. So it doesn't have tabs on the top side like the Tesla Model 3 has. When you crush, the high voltage bus bars are not in danger of getting short-circuited. So to look at the side integration in the battery pack, battery positioning, we can see the Han has a slight side seal here that is used for mounting. It's an extruded part, and then it goes directly into the tray. The tray is 16 millimeters, so it's medium size thick, and it has only on the rear side, it has this extrusion profile here for the second floor. So this is only under the rear seats, the second floor that you can see here. The front seats and under the main area, it's only one floor. And the cooling system is actually on top of the cells. Not like with the other packs where the cooling system is between or underneath the cells. Here the cooling system is on top of the lower layer of cells. And bottom protection plate, 2 millimeters, 3 millimeters, like in most vehicles. So here, quite state of the art. What does that then give in terms of cell weight to battery or tray weight? And that's quite interesting. Actually, it's the lowest number we have seen so far. So here, the cell-to-pack approach really comes into full play. And we see only 13% of the cell weight is actually in tray weight. That's even undergoing the Tesla with about 18%, even though it has the same base plate thickness, even a little bit more in terms of 4 millimeters compared to 3.2 millimeters, and it has the same underfloor to cell ratio as the Tesla Model 3. So here, definitely the cell-to-pack plays out, and we can look at the cell, if the cell can actually take all those forces that might go in its direction due to crash and so on. We put the cells into crush. You can see on the right side this very long cell. Actually, this is more than a meter of cell with more than a kilowatt-hour of content. So it was quite interesting to actually do all the abuse tests on it. But it survived quite well, so no issues on the crush, not really issues on nail penetration. Thermal stability, here we had a reaction, so you can see the cell is quite dark, and also the cell is bubbled up, so it's actually similar reaction to what the Neo ES8 showed in terms of strength. Electrical short circuit, all the cells survived quite well. Then the overcharge test, here also cells survived quite well, a little bit bubbled. So in total we can say that the Han cell actually has no safety level beyond 4 as of current testing, which is better than the NMC cells, especially for nail and overcharge. On the other hand side, for the nail penetration testing, the maximum temperature that LFP shows definitely not even is close to what the large cells, what the NMC cells are providing, even though the cell itself, the Han cell itself, is a quite large cell, and there is a significant amount of electrochemistry that is being shorted by the nail. So here we can see that the LFP cell actually is quite safe. On the other hand side, as I said, thermal stability, we're approaching nearly the same temperatures as with the NMC or NCA cells, a little bit better than little bit less good than the Taycan cell. So the Taycan cell still remains the cell with the highest thermal stability. Our conclusion here is that the thermal stability is not a cathode material issue so much as it is an electrolyte and separator issue. And I think we had some talks with a couple of suppliers over the last time, since the last presentation I gave on this separator issue, and just seeing what kind of complex structures are in there, you can really say that there is a lot of potential also in the separator and electrolyte mixtures in order to get the thermal stability right. But it is also a cost issue that you have to offset somewhere on your pack level in the end then. Yeah, for short circuit, we do have a hazard level 1, so nothing really happens. In this case, the protection is quite okay. And Tesla Model 3 has the same very short or very low reaction, but it has actually an in-cell measure to compensate for that. So in total, we can say the Han cell is a quite relaxed cell for integration, and it gives a good indication that LFP, when coming to the markets or being released to the markets in the next years, is a chemistry that you can implement into a battery pack with lowering actually the safety measures a little bit from the NMC world, and as such a very good candidate for the topic of cell to pack. In case there should still be some kind of issue, what is the thermal propagation inhibition measures that this cell to pack actually has implemented? And here we see a glass fiber mat with an aerogel that covers all the cells, including the thermal system. So it's above the thermal system. There is a mat over the whole battery inside the cover that actually protects from any hot spots or hot gases that might come out of the cells, protects the passenger compartment. And we also have a venting strategy here, venting and two breathing devices, venting devices, combined devices in the rear of the pack, so towards the chassis structure actually. So as expected, the pressure of the gases that are released will be quite low, and also the temperatures will probably be quite low. I think this opposed to on other packs where we have seen this venting towards the chassis, where it is more of a problem on the NMC world. Here we don't expect this to be a problem, and see it as a well-protected spot to place those breathing and venting devices. So what can we say in total around venting strategy and fire protection measures? There is a very close distance cell to cell on the Han with lower than 0.5 millimeters. There's just some electrical insulation between the poles, between the cells, and there is a very small venting surface. But yeah, as the gas generation is expected to be low, this is not a problem. On the other hand side, the very small distance between cells, also a little bit attributed to the LFP having less swelling and breathing than an NMC would have probably in the same size and format, and also the topic of its low safety rating are really playing into the topic of cell to pack quite nicely. One thing maybe to point out, which is interesting, if you ever thought about balancing on such a cell to pack where you have the pulls on the opposite side of the cells, you would have to have connection wires or some kind of FPC across the whole pack, basically to connect the two pulls for balancing. Interesting solution that BYD has chosen here to make the housing actually be the transmission pathway. So there is a separate pull on the housing that actually connects from the outside to the housing in order to have balancing hardware only on one side. and use the housing as transmission pathway for the balancing. That is also why there is a strict electrical insulation needed on each housing towards the chassis mass and also towards the next cell. So this is the 0.5 millimeters. Then talking about the electrical safety, we do have here a schematic comparison. So on the electric side, there is 2 melting fuses inside the Han pack, which is quite standard. There is 3 contactors, HV plus, HV minus, and pre-charge. And actually, we have seen on the integration slides and on the pack slides, there is bus bars inside the pack to connect the front of the pack with the rear of the pack. And there is also high voltage cables in the car integration in the middle tunnel that connects the front end of the car to the rear of the car. So here's probably also some space for optimization, for efficiency measures on the car and on the battery pack in order to not transmit the current forth and back over very long distances. There could be some architecture choices also that are different, but we would see some optimization potential here. On the overcurrent protection, we have the fuses, and you can see them integrated into the electric box right here. There is another one that is mid-pack, and there is 2 of the relays here and 1 on the rear section. On the touch protection of the whole pack, and we see IP-XXB on the Han, so quite standard, no surprises here. And oh yeah, you can see on the pack here, on the picture of the pack, you can see those large bus bars that are actually connecting the second floor to the front EE unit and the rear EE unit. So in total, for the safety parameters, I would say quite standard, no MSD. There is a melting fuse in there. Fuse location is in the junction box in the positive pathway. The short circuit, the current that is calculated here is actually 4.8 kiloamps, so it's quite a lot lower than on the other packs. And we believe that this is due to the higher voltage of the pack. There is less electrochemistry connected in series. In parallel, there is more of it connected in series to reach the 570 volts. And the power is the power is reduced. You can see 450 amps nominal versus the 700 to 800 amps that you either need on a 350 pack or on a quite high power pack like the Porsche Taycan. So overall, fuse significantly smaller in terms of weight, but the volume in length still significant due to the voltage. Yeah, with that, I want to conclude my presentation today on the safety and integration features of the BYD Han, a quite interesting vehicle, and I believe we will see much more of the cell-to-pack integration and new cell formats like this in the future, as there is definitive advantages and there is also some new risk balancing structures. So yeah, in total, I think quite a lot to be learned from such benchmarking. The next vehicle up will be the ID.3. It will be presented in AEBC Europe in Wiesbaden next year. And with that, I want to give you also the information about 2 more vehicles that we're actually benchmarking in China, the Wuling Mini EV and the River ER6, that are currently ongoing, in case you're interested in more of our Chinese market assessment. Thank you very much for today, and have a good conference, even though I cannot participate this year, as in Europe pandemic is ongoing. But I'm looking forward to summer next year in Europe, the AEBC, and the discussion later on with you. Thank you very much.